I am very happy to announce our next presenter, Dr. Tirath Raj, postdoctoral research associate at University of Illinois Urbana-Champaign, a Center of Advanced Bioenergy and Bioproducts Innovation, U.S. Department of Energy. The topic of today's presentation of Dr. Raj is bioenergy crops as a sustainable and renewable feedstock for biofuel and various value-added bioproducts. So, Dr. Raj, please, we welcome you at our conference. You can start.
Thank you very much for providing me this opportunity. So I'm Dr. Tirath Raj. I'm a postdoctoral researcher at University of Illinois, and I'm working at CABBI, Center for Advanced Bioenergy and Bioinnovation Center. So I will be discussing about the bioenergy crops today and their application for production of fuels, chemicals, and value-added products. So before going deep into the presentation, I'm briefly discussing about what we are, where we are located. So we are located at Chicago, Illinois state of United States. This center is established under US Government of Energy, and that is known as Center for Advanced Bioenergy and Bioinnovation at University of Illinois. There are almost 4 bioenergy research centers are there in United States, specifically, which are looking for renewable fuels production using different crops and different methodologies. So one of that center is CABBI. So recently this year, US government has refunded their funding for next 5 years. So here we will be discussing about, or here we will be working on production of bioenergy crops, because there is a huge competition between the food crops and this renewable crops. So here we are basically producing the energy crops and their application for production of fuels and chemicals. So I think this slides, everybody know why we are working that one, why there is a carbon importance for sustainability. We all know that there is a huge increase in GHG emissions like CO2. We have reached about 421 ppm by last year, and that is a huge in the century. And the global rise has an impact. Sorry, global rise has a huge impact in overall economy as well, because it increases the overall hottest temperature. Meanwhile, it increases the total soil erosion with the floods, and it also increases the wet precipitation changes. So there is a huge need to look for these carbon sequestration techniques. So mostly the industry or the scientist people, they are looking for some biological sequestration method, or they are implementing new biofuel policies to reduce the extra carbon generation. So in view of this, there are some lignocellulose crops, which is basically abundant worldwide, and they basically represent 3 basic polymers: cellulose, hemicellulose, lignin. Cellulose and hemicellulose are most abundant organic polymer in the nature, and that can be used to produce variety of products, like I mentioned, the bioplastics, sugars, fibers, some chemicals like lactic acid, glycerols, and this hemicellulose can be used to produce furan, acetic acid, and xylitol. Besides this lignin, this is another very important biopolymer, and that is basically a polyphenolic compounds. And due to this polyphenol compound, that can be used to produce variety of this phenol kind of resins or this polymers as well. So these biomass can be used to produce fuels and chemicals via using these 2 platforms, like sugar platform or this thermochemical platform. I will be discussing more about the this biochemical platform as compared to thermochemical. So if we see the scenario, IEA report by the end of this year that the total biofuel demand will be around 40% by 2030. And out of that, if we talk about in transportation fuel, the conventional fuel and the biodiesel, they are the major resource for that one. So if we talk about the comparison from 2022 to 2030, almost 40% increase will be there by for these fuels. So some initiatives have already been done in recent year from these 5 years. Like India, they mandate to blend up to 20% by 2025. Brazil, they plan to increase their biodiesel blending by 15% by 2026. Similarly, United States have implemented very new policies, and they are financing a lot of money in renewable fuels production. Canada also mandated to reduce 13% of their GHG by 2030. So likewise, most of the countries, they have mandate and they have releasing new updates to reduce in overall carbon emissions to achieve a net zero target. So if we talk about the biochemical processes and challenges, this is a simple overview how this biomass can be used to produce a biofuel. Like here we see the lignocellulosic biomass that can be pre-processed. It can be collected from the field, storage can be reduced for the size, and then after pre-processing, it can be used to deconstruct. Because in the lignocellulosic biomass, the polymeric components are highly recalcitrant. They are bind in together in a very highly recalcitrant matrix of cellulose, hemicellulose, lignin, via strong chemical and this hydrogen bonding. So they are not easily available for the microbes to digest them and to produce the sugars for downstream processing. So if we talk about the lignocellulosic biomass, there is a prerequisite need for this pretreatment. That is called pretreatment. We treat the biomass with certain agent, we releases the sugars, polymeric sugar, and that makes it available for the downstream processing. So another is a on-site enzyme production, followed by the biomass hydrolysis, and then the microbial fermentation to produce the fuels and chemicals. So these are the basic unitary operations during this overall biochemical process. And if we see the techno-economic of oral process, we see the biomass pretreatment and the downstream cogeneration cost a lot. That's why if we talk about the pretreatment, it almost costs about 20% of the overall processing, and 10% is for the feedstock. This is a major challenge because we do not have a complete, sustainable feedstock which is available throughout the year. And second is the lack of proper pre-processing technology like the pretreatment. So if this table summarizes the global facility and their current status in cellulosic ethanol production, if we talk only the cellulosic ethanol production, so you can see on the red column, most of this company, either they are on hold or they suspended their operations with their production, and they have targeted to achieve different kind of ethanol production in upcoming year. And this column demonstrated the bio feedstock what they are using. So if you see this yellow column, most of the company, they are either hold because they are having some financial issues, or their lack of continuous feedstock supply. Beside that, there is a lack of proper bioprocessing technology. And some of the companies, they are facing highly financial crisis due to high energy and cost input. So there is a need to look some renewable energy resources and greener pre-processing methods. This table summarizes the pretreatment method used by commercial bioethanol plants in the United States, like Abengoa, Praz in India, DuPont, Beauregard, Clariant, Beta Renewable in Italy, AP Biorefinery in the United States, and Point DSM in the United States. You can easily see most of this company, they are either using this acid-based method to deconstruct the biomass, like the mixed acid, sulfuric acid, or H2SO4, and some of them, they are using either SO2. So by using this acid to deconstruct the biomass, they are releasing certain amount of bioproducts, or certain amount of undesirable acids, which basically impact in downstream processing because they increases the overall pH and they generate some inhibitors during the processing of the sugars. Hence, they impacted the growth of microorganisms. That's why most of the company, they are either on the hold or either on the shutdown phases. Second crisis is the funding process, or the financial issues, or the feedstock supply. Like here, as I mentioned, Abengoa, they are using wheat straw. Whereas in India, they are looking for the multi-feedstock technology. I think this year or next year, they are going to set up a biorefinery plants in India based upon rice straw. And DuPont, they are using corn stover. Beauregard, they are using sugarcane bagasse. If we compare the scenario with Brazil, in Brazil, most of this ethanol is produced from sugarcane juice. However, if we talk about Europe, they prefer mostly this wheat straw or corn stover. But if we talk about the United States, most of the company in the United States, they are looking for the corn-based processing method, or that is the first generation process. So processing of lignocellulosic biomass is very challenging. So I have tried to mention some green method of deconstruction which can be recycled, and if they are completely recyclable, the cost of processing may be reduced or even can go to zero. So one of this is NADES, that is called natural deep eutectic solvents. They are basically a mixture of hydrogen bond acceptor and hydrogen bond donor and meets the green solvent criteria. So they are basically some kind of chemicals, some kind of solvents that can be easily derived from some natural resources, and they are environmentally benign. Like they have the low negligible vapor pressures, renewable solvent characteristics, and greener substrate for toxic organic solvents. If we recycle that completely, even because they have a very low vapor pressure and it can be recycled well, even 100%. So we can recycle it multiple times. So overall processing cost will be zero. And they didn't release any kind of toxins during the pre-processing of that one. So here are some NADS example like choline chloride, lactic acid. This is hydrogen bond donor. This is acceptor. Similarly, oxalic acid and glycerol. Why I'm emphasizing this one? Because lactic acid, oxalic acid, glycerol, and chlorine chloride, they all can be derived from biomass itself. So try to make a closed loop biorefinery. It means we are not using petroleum-based solvents. We are just producing these solvents from the biomass and reusing that to pre-process the biomass. Like if we talk about the glycerol, that is the byproduct in biodiesel biodiesel production. Sorry. And the oxalic acid and lactic acid, like lactic acid can easily be fermented from these sugars by using microbes. So this lactic acid either can be used go for the polymerization or can be used to produce the NADS. So ultimately these solvents have very unique characteristics. They can interact with cell wall components and can selectively extract out the sugars from the biomass. So this is, I try to present this NADS based biorefinery. So we have submitted a manuscript based upon this data, and we have showed that this NADS can be recycled 100%. So these NADS can be synthesized from the biomass, and then in NADS based pre-treatment method, they can be used to treat the biomass. And after pre-treatment, the cellulose rich pulp is like that can be undergo for the enzymatic hydrolysis to produce sugar. And that can also be used to produce the lipids. I will discuss about how it comes from the cellulose to lipids. And the pre-treated liquid, which is selectively enriched in lignin, can be precipitate out to produce the value-added products, because this lignin is highly polyphenolic compounds and that is pure. And this NADS in the liquid phase can be recycled back. So we tested in the laboratory almost 5 to 10 times. We can recycle that NADS and reuse that one. So there is no wastage of water, no generation of byproducts, and no loss in efficiency. So we try to postulate a methodology or biorefinery using NADS, where there is no generation of byproducts and almost 80 to 90% of the sugar yield will be there. Another is the ionic liquid, as the term says, the ionic and the liquid. If you see the common salt, NaCl, that is also ionic, but the problem is that this is, the melting temperature is very high. They remain solid at the room temperature. However, in case of ionic liquid, they remain ionic at the room temperature. So they basically consist of organic cation or inorganic anion, and typically they work or they remain liquid between 90 to 150 degrees Celsius. Similarly, they have negligible vapor pressure, low volatility, and good thermal and chemical stability. They also have a unique characteristic that is called solochromatic property, solvent characteristic. They also interact with this cellulose, hemicellulose, or lignin. So what happened in the nature, these three components, they bind very strongly. So what happened when we insert this ionic liquid, they open the structure and releasing these components in different phase. So I have tested this imidazolium based ionic liquids, colonium based ionic liquids, and this colonium lysine or acetate based ionic liquids. We synthesize in the laboratory. We have used that one, and we have tried to find how much sugar we can extract after pre-processing of this biomass. So this is another, what is the mechanism behind this biomass solubilization in NADS? Here you can see this imidazolium based ionic liquid, which consists of this hydrogen and ion. They can interact with the cellulose chain wall through hydrogen bonding, and by that there is a competitive hydrogen bonding between these cell wall components and this ionic liquid and the cellulose. So what happened, they bind it, they extract into the media, and after using some solvent, we can recover this sugar, polymeric sugar, and that can be easily digestible by the microbes during the enzymatic hydrolysis to produce a sugar. And if we have a pure sugar, it can be used to produce n number of products during the fermentation and during the thermochemical processing as well. Like we can use that to ferment to produce a lactic acid, succinic acid, even the PHA, many things we can use synthesize from the glucose. So idea is to how to produce more and more glucose from this biomass. So this is all mechanism, how it works. If we see the cellulose chain, in nature, cellulose in biomass is either in the cellulose 1, cellulose 2, cellulose 3. Cellulose 1 is highly recalcitrant in the structure because they have presence of these 3 specific bondings, 3 OH, 5, 2 OH, 2 O6. If you see the numbering from here, 1, 2, 3, 4, 5, 6. So based upon that, these 3 interaction bonding, they have a very limited or low, intermolecular hydrogen bonding gaps, like 1 to 2 angstrom in between 2 chains. So if we do the enzymatic hydrolysis, it's very hard to fit this enzyme into that cavity. So what happened, when we do the pretreatment using ionic liquid, they open up the cell wall structure, and hence they are increasing the overall the chain length in between these 2 chains, and that is about 3 to 4 angstrom. And this size is related to the size of enzyme. So enzyme can easily fit into that cavity, and it can hydrolyze this beta glycosidic linkage, hence opening the cell structure of this cellulose. Now we talk about triacylglycerols. If we talk about the energy content of different resources like protein, sucrose, ethanol, vegetable oils, biodiesel, petroleum diesel, here is the energy content. Like petroleum diesel has the higher energy content, like 43, but we are looking for the alternative due to this, limited supply of this petrol-based resources. So if we talk about this biodiesel and the vegetative oil, so they have almost 37.1 kilojoule per gram of energy. And if somehow most of the biodiesel nowadays that is produced from either oil seed crops, like soybean seeds or canola seeds or corn oil, but they are not able to supplement the demand of biodiesel nowadays. And this biodiesel is nowadays preferred for this aviation turbine fuels due to this higher calorific value. So, and we are trying to replace this petrol-based biodiesel. So in this main, these are the fatty acids, triacylglycerols. They are basically synthesized in lignocellulosic biomass as well. So what happened, in our laboratory, researchers have done some study, and they have changed the carbon flux in the lignocellulosic biomass to divert the carbon pathway to synthesize the oil in the lignocellulosic crops as well, as compared to the oil seed. If you remember, the most of the oil in the crops is either in the form of oil seed or they are in the leaves as well. So here we are using some new methodology. We are trying to accumulate the oil in the vegetative tissue of these crops. So this data shows there is a huge demand of these tags for renewable diesel. As I mentioned, these diesel are mostly preferred for the sustainable fuels. So if somehow we reduce almost 20% of biodiesel demand, and somehow we replace the biodiesel by 20% of this renewable biodiesel, we can replace almost 20% of the emission by 2030. So the fats and vegetables are basically used to produce the biodiesel. The technology is there, the processing is there, how to produce the biodiesel from the oil and the fats is there. But the problem is the supply of the feedstock. So we just need to provide a good feedstock to produce more and more oil in that one. So what we are doing, the CABBI researchers have transgenically engineered some crops. As I mentioned, I will talking about the bioenergy crops. So this is related to the bioenergy crops. So at the CABBI, the engineer they have metabolically engineered some crops like miscanthus, soybean, sugarcane, and they have changed the carbon flux to accumulate up to 5 to 10% of oil into these bioenergy crops. So idea is to synthesize or change the carbon flux to accumulate more lipids into the vegetable crops, and that can be used to extract the oils for production of biodiesel or renewable diesel. So our challenge is to accumulate 10% of the oil in sorghum of the biomass on dry weight per hectare. So if we are able to achieve 10% oil in the sugar crop, we are able to achieve 184 gallon of vegetable oil per hectare. And that is sufficient to replace almost all petrol-based biodiesel. Like if we talk about the sunflower, almost 25% or 20-25% oil is there. If we talk about the mustard oil, or if we talk about the corn oil, almost, if in a corn kernel, if we say 4 to 5% oil is there in a particular corn kernel. So see here, if somehow we are able to accumulate 10% of the oil in the sorghum crop, which is a bioenergy crop, then we can replace almost most of the petrol-based biodiesel. So the idea was that. So what we are doing at the CABBI, as I mentioned, CABBI is the center funded by US Government of Energy, and we are working on the bioenergy crops. So here what we have done, we have selected 3 crops: sorghum, sugarcane, and miscanthus. So sugarcane is like, this is a mostly grown crop worldwide, and that is basically used to produce the sugarcane juice or bagasse. So like in Brazil, most of the cellulosic ethanol refinery, they are using this sugarcane juice. And so they have genetically modified the sugarcane in such a way that produces more amount of juice in that one. So they are extracting that juice and fermenting to produce the biodiesel, or this bioethanol, sorry. However, in our case, what we have done, that's why we have selected the sugarcane. So we have done some metabolic engineering, and we have changed the carbon flux in these crops to accumulate more and more oil in this crop with the sugars. That's the beauty of this, overall techniques. So by using the metabolic process, engineering, breeding, we are accumulating this oil and sugars in the plants, and we can extract these sugars and the lipids from the bagasse or from the biomass, and these can be used to produce different kind of like biodiesel or this bioethanol during the processing. So here, yeah, 3 crops, as I mentioned, sugarcane, this miscanthus, and oil can be recovered, the sugar can be recovered, they can be used to produce, like sugar can be used to produce ethanol, oil can be used to produce this fatty acid for the biodiesel application. So here, I mentioned this, yeah, we are using the sweet sorghum, miscanthus, oil cane. We named as oil cane. You will not find, so much detail on that oil cane. Our center is only working on that oil cane. That is nothing but a genetically engineered sugar cane, which is engineered to accumulate oil. So we named as a oil cane. Similarly, switchgrass. So these are the advantages. These crops can be grown on a marginal land. We have studied and we have found we have big field at the United States in the laboratory as well. So what we do, we perform some experiment in the laboratory first, and then we try to plant these crops in the open field. So we have 2 fields, the Florida and Illinois. We grow their crop and try to do some study, harvest them, and then we process in the laboratory. So these crops can be grown on the marginal land, which is not suitable for the food production. Like that is empty and the land quality is not good to produce the food. So we can use that land to produce the bioenergy crops. And they have some environmental benefits. A study found that they are help in erosion prevention. They have very limited soil nutrient this requirement. And they also increases soil fertility by accumulating the carbon and nitrogen into the soil. And they are basically free from food versus feed debate. We are not growing for food. Like if we grow this wheat, we are growing the wheat and corn for production of food, but we are using the residue. So in that way, we have to focus either on the food side or the feed side. But here, these crops can be usually grown on marginal lands without a required of nitrogen or this water need for that one. Like they have a low water content, required nitrogen content, and they also help in establishment of this carbon neutral potential. And they are known for efficient carbon sequester in the soil. That's why I mentioned that if these crops can be grown in any part of world, that can be helpful in overall restoration of soil, restoration of economic balance, and production of renewable fuels and chemicals. So in that, these crops have a huge benefits in overall, like in terms of economy, in terms of sustainability, in terms of production of fuels and chemicals. So I have mentioned one crop like oil cane, that is a bioengineering crop, and we have engineered that crop in such a way to accumulate lipid with the sugars juice. So these lipids are accumulated in the node of the sugarcane with the juice. So these lipids and sugars can be extracted to produce the material, chemicals, and fuels. So these lipids are basically triacylglycerols, and these are stored in the plant body. So if you need, you can go to that article, you can find more information how they have changed the carbon flux to produce this sugar pathway to this lipid pathway, how they change the sucrose to lipid. So that is very interesting paper. I think 3 to 4 years before the researcher have developed that one. Now we are trying to increase and more oil content in that sugarcane. So here, this is one example how we are processing. So we are growing this oil cane in the open field. We are collecting after 4 to 5 months this oil cane steam, and then we are just pressing to recover the juice, which is consist of little amount of oil and the bagasse. So the oil or the composition, if we see the overall composition of the bagasse, almost 30 to 39% of glucose is there, 15 to 22% of xylene, 2 to 5% acetyl, and 16 to 22% lignin. Beside that, there is a 3 to 5% of tag is there. This is triacylglycerol. This is the beauty. So we can recover almost 3 to 5% of triacylglycerol with respect to sugars. So we can use that one, and we have seen that this bagasse after juicing can be used to pre-process after grinding, moisture adjustment, pre-treatment. So we are using non-chemical free, like we are using hydrothermal pre-treatment. We are just treating this bagasse after juicing at a particular temperature of 170 to 200 degrees Celsius without addition of any acid. Like most of the commercial enterprises, they are using dilute acid, as I mentioned, or sulfuric acid. They are producing huge amount of bioproducts or toxins. So here we are using hydrothermal pretreatment. So what we do, we just take the bagasse at particular solid loading of 10 to 50%, add the water, heat it in a pressurized system. So under high pressure condition of 4 to 5 bar at 170 degrees Celsius, the structural changes happens. So what happened after dismilling, we do the hydrolysis, and we achieve that almost 80 to 90% of the sugar can be achieved from the bagasse. So this is one side, and another side is the juicing side. From the juice, we can easily use to ferment, because this is a sucrose, mainly sucrose, that can be used to ferment that one. And this is the total lipid profile in that dry bagasse and the after saccharification. You see in the untreated and the hydrothermal treated bagasse at 170 for 10 minute 10 minute 200 degrees Celsius at high temperature and high resistance time. You can see almost 3% of total bagasse consists of lipids. It means in overall, if we weight basis, say 100 gram of oil cane have almost 33% of this lipid is there. And even lipids, because they are hydrophobic in the nature, they doesn't come with the juicing. Almost 0.05% of the lipids come during the juicing process. Most of the lipid remain in the bagasse. So we can use that bagasse to recover the lipids. So you can see here from here the lipid present in the dry biomass and the lipid present in the biomass after saccharification. So it doesn't go anywhere; it remains there. So we can recover that lipid after pre-processing of that one. And we have found that hydrothermal pretreatment of this bagasse at 170 degrees Celsius, we can accumulate almost 25% of total lipids in the pretreated liquid, and the rest of this lipids is either accumulated in the bagasse or remain in the residue, this fermented residue or saccharification residue, like in the this lignin residue. And total 80% of the sugar can be achieved during this hydrothermal pretreatment. So I have tried to show that the importance of this bioenergy crops, and try to see one example of this oil cane, which is the most emerging crops, because they can be easily grown in any marginal land. So taking the scenario, we have tried to do some exercise, grow in the laboratory. We have 3 groups in our groups: conversion, theme, and sustainability. So I'm in the conversion. So we basically process this biomass from the field to the laboratory, and we have a pilot scale facility for the hydrothermal pretreatment. So we are processing that one. So beside that hydrothermal, we are treating this bagasse and the oil cane with respect to these green solvents to make the economy feasible. So this is our conclusion. The bioenergy crops like oil sorghum can be financially and environmentally favorable as compared to traditional sugarcane. They can be grown very easily on the marginal lands, and we have developed some green methods of pretreatment such as hydrothermal NADS and ionic liquids, which can improve the overall performance and the yield of sugar and the lipid. And these crops have higher potential for economic sustainability, because we are all looking nowadays for economic sustainability and restoration due to greater demand of renewable fuels like ethanol and biodiesel. The feedstock oil content is very important in overall. So although the oil content in this crops is 3 to 5% nowadays, but the further metabolic engineering can help to improve it further to achieve our target to 10%, to make it more economically and environmentally favorable. So yeah, that is all about from for my presentation for today. I'm open for the questions. Yeah, thank you very much for the opportunity.
Thank you very much, Dr. Raj, for this very informative presentation and a lot of hopes in further promoting bioenergy production with your solvent and your transgenic crops. Are there any questions from participants? Please unmute yourself and ask if there are any. And while we are waiting first question, maybe I will ask mine. I'm not myself an expert in bioenergy, but do I understand correctly that some amount of oil or triacid glycerol is already present in these most popular bioenergy crops, but they are not currently extracted, so only sugars are used for bioethanol production, but not these lipids?
Yeah, you're right. They are presented in very small, because I think in every plant they synthesize the lipids.
But not in the seeds, but in the like stems and leaves.
Yeah. So they are basically produced in some metabolic pathway to accumulate the energy for the future use, like for the regeneration use or propagation use. So idea was to replace some genes in overall metabolic process, so that we can we can transfer the carbon flux to produce more and more this oil in that one. So our center have done that study, and we have changed some genetic manipulation in that one using the metabolic techniques, and we have tried to accumulate more and more lipid in that one. So idea was that like most of the people, they are looking for the biodiesel, and we don't have the continuous supply. If we see this oil or this biodiesel, they are basically produced either from jatropha in the past, and a year before they are using jatropha, the soybean oil, the carengia oil, but they are not enough. Even the oil content, if you see the seeds, are almost only 20%, maximum 20 to 25%, not beyond that one. So in the energy crops, because as I mentioned, these are the energy crops, they can be easily grown, and they are benefited with that we can grow for the sugar, but we can recover the oil. So idea was to to produce a single crop which can supplement most of the energy need with a limited supply of nutrients, minimum supply of this soil fertility requirement, and that thing. Yeah.
Thank you. Are there any questions from participants? Please unmute and ask. Okay, then I have another question. So do I understand correctly that in these transgenic crops, the amount of sugars somehow decreased because you increased the oil lipid production?
Not so much. Very little is decreased, yeah, because they balance with that one, and almost 30 to 39% of the sugar is there.
I see.
Yeah. In overall crops, this is the range, 30 to 35% sugar is there if we talk about glucose only. But if we talk about in overall, almost 50 to 55% of sugar is there, including cellulose and hemicellulose. The problem is how to extract more and more amount of sugar. Like in our process, using the hydrothermal, we are able to recover almost 80 to 90% of sugar from the particular biomass. Yeah.
And then my question is also, so you made these transgenic crops more productive. But you also mentioned that you can grow them on marginal land without fertilization. So I wonder, because our previous presenter on bioenergy crops, they highlighted many times that in order to have commercial production of bioenergy, so we mostly discussed about combustion, you need to apply some fertilization. We mostly talk about sewage. But what is about the crops which you mentioned? Do you really need an additional fertilization, or you can really use like just this marginal lands with no or very few fertilization?
So in our group, we have a field I visited 2 times. So what they are doing, so they have categorized the field. So they are supplementing some nitrogen like NPK fertilizer or urea. So the study is still on, on the preliminary layer. So they are basically understanding the impact of this nitrogen need for the particular crop. So we are growing these different crops. I think we recently published a crop, and it mentioned that it doesn't impacted the overall this carbon and nitrogen need requirement. So based upon that, I concluded that okay, these crops have very minimal requirement of this nitrogen as compared to the conventional crops.
Okay, interesting. And then my question is, so maybe I just combine two questions in one. Like first part is there like easier certification for a transgenic bioenergy crop? This is the first part of the question. And the second, if this metabolic pathway is already existing in the crop, in countries like Ukraine, where transgenic crops are forbidden, is it possible to select lines, varieties which has naturally high production of lipids? Like, is it promising, or we cannot achieve sufficiently high level of lipids without transgenic modification?
The question is from me?
Yeah.
Okay. Yeah, I think everybody know about the Ukraine condition. It depends upon the weather as well. So weather and soil are the two important factors. So there might be some hit and trials experiment may be needed during this growing crop. So because we did this study from last I think 5 to 10 years, and we have achieved almost 3 to 5% oil in that one. So the goal is to achieve 10%. But we till date we came up to 3 to 5% oil in that one. But we have seen, okay, with respect to one by one step improvement, we can achieve that one. So if we take the scenario for the Ukraine, based upon the weather condition, we can try to grow these crops initially on giving the high this nitrogen and carbon input to these crops, and then we can try to make them adapt. Okay, and because we are not sure that whether they will die or whether they will grow, or if they are growing, either they are producing this oil in that one or not. So this is like some kind of this adaptivity. So we have to make some trials in that particular land area, and we have to try to check this soil condition as well. What is the salt condition in that soil is there? Like after military operation, maybe there is an increase in the acidity of the soil. Maybe there is an increase in the salt concentration in that one, which may impact the overall carbon flux in that soil. So it's not a thumb rule. So we have to do some hit and trial experiments with the crops. But nature always balance themselves by themselves. So my suggestion is to try the crops in some laboratory area and try to maintain the a particular soil condition as we grow here. So and then try to mix the soil with respect to your soil. So so you can adapt the crops with respect to the atmosphere. So if they grow well, that will be good.
Because like I just recall another research, it's on bioenergy crop, but it's woody crop, and they tried to reduce the level, I think, of hemicellulose by transgenic methods, but finally the solution was just to go to the nature and find the line which exists in the nature, which already has naturally lower number of this hemicellulose. So that's I think that this could be like
I did some study. We cannot reduce, in my opinion, we cannot reduce overall production of hemicellulose. Even I did work with some people in California at San Diego Laboratory. They tried to minimize the production of lignin in their biomass. So if we remove the lignin percentage in the particular biomass, there may be chances of, they cannot sustain, because the lignin provides support to the growing plant. So, and this is a, polyphilic polymer. Similarly, if we remove or if we reduce the production of hemicellulose, what happened? It will reduce the rigidity of the plant. So in my opinion, we can do one thing, we can increase the production of these sugars in that one. And secondly, we can, design some process which can use to extract more amount of sugars. And even I don't think why we are reducing the hemicellulose, because this is a C5 and this C5 can also be fermented. So if
I think that they use it for paper, so they have like a little bit different.
Okay. But in my knowledge, because I saw most of the crops, if we talk about in terms of sugars, almost 60% of sugar is there if we combine cellulose and hemicellulose. Although there is a very less percentage of strains are available which ferment this hemicelluloses exactly. But in hemicellulose, there are some arabinose C6 and C5 sugars are there, but there is a limited strains are available which ferment the C5 sugars. So if somehow we design some, fermenting strains which can ferment the C5 and C6 as well in together, then we can increase all our productivity. That's my idea.
That's a very interesting idea. So are there any questions from participants? Please use this opportunity, unmute yourself and ask. Okay, then my final question is, do I, on current bioethanol production facilities, is it possible to use different kinds of like feedstock or raw material, or are they designed in a way that they are the most efficient with like specific type of the raw material, like this corn, straw?
Yeah, I came from the industry. I just give a brief summary or just say information. I came from India 5 or 6 years before. I work at Indian Oil Corporation R&D Center. This is a 500 Fortune company, and they are going to establish a biorefinery plants based upon dilute acid pretreatment. So I work on that one. We have an aerial based 3-story building, an aerial this H2SO4 plant, and we have used rice straw as a feedstock. So we tested different crops for a particular technology. Like if we are using dilute acid pretreatment processing method and you are using rice straw or corn cob, the biomass nature is different. The thing is that biomass nature is very different. If you are using the corn cob or corn straw, when we try to make a plug, it doesn't make a plug because it feels like a slippery. It doesn't pass through this, hopper, and it doesn't make a plug during the processing because it is stick at a particular position. So we try to do some experiment by using the mixing that crop in 2 or 3 combination, because like one crop cannot be available throughout the year. So what we have done, we have used rice straw because it has some silica. It makes some, create some restriction to the fables, and it try to push the biomass into the next stage. So what we do, we mix this rice straw with certain amount of this corn cob or corn stover, and we can process that one. But there is a lack of technology. Even in the United States, I saw most of the plants, they are focusing on one particular corn. So idea was that they did either they tested it or the processing technology is specific for the pretreatment. But in my knowledge, we can use the multi-feedstock pretreatment technology to process the biomass in combination, because we are just focusing on the sugar side. We are not focusing on the biomass composition size. So if in overall we mix that in particular ratio, so there is a combination ratio. If we tried like rice straw, corn cob, or corn stover, we mix into 1:2 to 3 ratio, we can process it. That's my way. We can process it. It's not an obstacle, but we need to make certain combinations for that.
Yeah, because like for us, because many of us come from the side of diversified agriculture, of course, we would like to promote the cultivation of diverse crops, including bioenergy crops. So it would be, of course, very good to have facility which can process different kind of materials. So we are looking for this research. So unless there are Any questions for Professor Raj? I would like to thank you very much for your very informative presentations. Also, our presenters, participants, thank you in the comments. And now I switch back to Ukrainian language.
Oh, yeah. Thank you very much for this opportunity, Rihanna. I thank to Rihanna very well. So she communicated me well. So, but somehow I'm available. This is almost morning 8 now for me. So
yeah, thank you very much for finding the
much.
time to present at our conference.
Yeah, thank you. Yeah.
Thank you.
Thank you. Yeah.